Welcome, everybody. Today's webinar is entitled Getting the Data, Location, and Equipment Right for Quality Water Well Drilling. And I'm going to be the moderator today. My name is Derek Chitwood, and I am the Senior Manager for Engineering Innovation at Water Mission here in the United States. It's difficult to overestimate how important it is to conduct thorough depth studies, use the right methods and equipment to determine how to drill or where to drill, and then use the right equipment to produce high quality water wells that function for the foreseeable future. In today's talk, we're going to be going over many of these details. The agenda today is that we're going to have opening remarks by Laura Holliday, and then two longer presentations, one by Dr. Martin Oduve on borehole siting fundamentals, and then a second presentation by Brandon Stone entitled Choosing the Right Drilling Equipment. And then, as I mentioned before, we're going to have some Q&A time, about 15 minutes of Q&A time before the closing remarks. So we'd like to start with Laura Holliday. She is a hydrogeologist with the British Geological Survey. She brings hands-on experience in borehole siting, drilling supervision, and groundwater monitoring across Africa, the Middle East, South Asia, including in fragile and water insecure regions. Laura?
Hello, everybody. Thank you, Derek, for the introduction. So I'm here today to introduce you to challenges in borehole siting and the importance of selecting the right equipment. Next. So as we all know, groundwater is a critical resource for rural water supply. But despite decades of improvement in knowledge and technology, we still see a significant number of boreholes failing and underperforming. Sadly, the consequences of this are pretty significant. So they include wasted time and investment, reduced confidence and trust from communities, but most importantly, delayed or limited access to water. And the real question is, why does this keep happening? Next. So in reality, borehole failure is not often caused by just one single issue. It's usually the result of multiple decisions made throughout the process. To start with, there's often a lack of data and understanding. Desk studies might be incomplete, and the data that is available might be low quality or misinterpreted. This means that decisions are being made without a clear understanding of the hydrogeological setting. This then feeds through into improper siting and decision making, with locations often selected too quickly or based on limited information. In practice, siting should really combine multiple data sources. That might include field data collection, for example, geophysical surveying in more complex environments, but this doesn't always happen. There's also challenges related to drilling and equipment, where equipment might not be suitable for the hydrogeological environment, and the quality of drilling equipment and borehole consumables can also vary quite significantly. At the same time, data collection during drilling might be poor or incomplete, and importantly, also borehole design isn't generally adapted to the site conditions, where the reality is that borehole design should be quite flexible, so we could be updating screened intervals based on what's actually encountered during the drilling process. And finally, all of this sits within practical constraints that do vary between project and location. So that might include limited budgets on a project, pressure to drill quickly, and then there's the many varied challenges of working in remote and difficult environments. So essentially, failure is often the result of a series of small issues at different stages throughout the process, rather than just one single problem at the point of drilling and installation. Next. So now we've looked at where things go wrong, we want to know what actually helps things to go right. The main message is fairly simple. Good siting, good design, and appropriate equipment leads to higher success rates and long-term sustainability. Good siting and design means building a clear understanding of the hydrogeological context that can be using both desk studies and collecting new field data, and then combining these multiple sources of information. But it also means continuing to collect and use data during drilling and ensuring that the borehole design is site-specific and adaptable based on what's actually being encountered. At the same time, appropriate equipment is not just about the drill rig, it includes the full construction process. This means using the right drilling method and suitable and well-maintained equipment to start with, but it also means selecting appropriate and good quality materials for installation within the borehole. So this might be the casing, the screens, the gravel packs, and even choosing the right pump. So overall, we can see that success comes from combining multiple informed decisions throughout the siting, drilling, and installation process. Thank you for your time, and I will now hand you back over to Derek.
Thank you so much, Laura. That was a great introduction. Greatly appreciate that. Our next speaker is Dr. Martin Uduve. He is a consultant hydrogeologist and managing director of MEV Hydrosearch and Engineering Services Limited. He comes with an amazing amount of experience, 43 years in geophysics, hydrogeology, and water resources. He also brings deep expertise in groundwater investigation, development, and integrated water resource management across both urban and rural contexts. Dr. Uduve?
Yeah, thank you very much. Just as elaborated in the beginning, quite a lot of this problem. How do we solve them? They haven't in terms of how to go about it. Next. 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 Yeah, sorry. Moving too fast. The second slide, please. Okay. These are the different situations that you actually find. You find people trekking quite a long distance, very unsuitable water that is contaminated. You have areas with a lot of surface water that has been contaminated. And of course, you have the only sometimes single wells that are managed with about 20 people trying to get the resource. Then, of course, you have even drainages that are filled with a lot of drains. You also have quite a lot of water that you don't even, that is not fit for consumption. And sometimes you have to wait for aquifers to fully recharge. Next. In some situations, for example, even in urban areas, this example from Lusaka, where you have both siting and, of course, pit latrines and other sorts of latrine all coexist together. And these are tapping shallow aquifers, and especially during the rainy season, there's kind of hydraulic connections, and this form quite a lot of contamination. Next. How do we go about this? There have to be a systematic way of doing it in terms of one, deck study, looking at aerial photograph, for example, looking at PACS results, looking at logs, looking at even satellite images and photo interpretations. You add that with most of the borehole logs that are available. You look at the geology, which is very important. By the time you combine both the deck study plus the recognition and, of course, the field work in terms of the geology, and combining that with geophysics, you're able to move forward in terms of good siting. Next. What are we looking for? This is the position of groundwater. At the top of the surface there, you have everything that happens, your buildings, your recreational services, and all your development issues. Then just below that, you have the soil water that gives you the saturated zone until you meet the static water level before you get to the saturation after the water level. Next. The basic issues that are very important, especially in locating good areas for siting, the geology itself, which I refer as the main housing unit. Generally, you have the basement complex and the sedimentary environment. Most of the aquifers, which are normally the geological formation that can store and transmit these very scarce commodity, has, for example, like fissures and cracks with the Precambrian basement complex. You also have some pore spaces within the sedimentary environment and a little bit of loose sand that are normally associated in water plain area, sometimes referred to as a fadama. Next. As geologically speaking, the first one gives the unconsolidated pore spaces, followed by the thoracic aquifers with the consolidated rocks. They are quite important, except there are fractures. Then, of course, you have what we call the karst aquifers. These are mainly silicified, calcite, for example, in terms of limestone and, of course, and dolomites. The calcium and, of course, the magnesium equivalent. And when there are fractures within this geological diversity, you have good aquifers. Next. In generally speaking, I've tried as much as possible to give the whole journey in a very good slide here. The first one talks about the depth studying and, of course, the area that are quite important, like the photo maps, the satellite, and, of course, most of the fractures. From there, you're moving into the feed aspect of it that identifies streams, that identify rivers, that identifies most of the aquifer itself, and including hydrographs, and of course, rainfall data that can be used to interpret this, then followed up by geophysical interpretation. Right in the field, when you notice that there is good prospect for it, then you can go on to do the siting. But if you are not convinced, you might have to go back and do more studies. Next. The geological environment is very important. Giving an example of a geological environment in Nigeria, where you have the sedimentary environment, the basement complex, and of course, the basement complex is mainly the granitic rock, for example, that is the igneous and probably the metamorphic rocks. All these are subject to the increase in terms of fractures and cracks that we're able to kind of identify areas where there are fractures. Next. Sometimes the geological map, people look at it as not very important, but these are direct evidence that can give you the direction of flow of most of the rock unit. Next. You can go into the cross-sectional areas, and these are very important because they directly identify those areas that are fractures and those areas you do not have fractures. And that is why it's very important to have a kind of very good look in terms of the hydrological section that we're able to identify areas to drill. Next. Now, the geophysical aspect is very important. It has always been very important. Having done your normal deck study, your recognition and field study, the next important aspect is to do the geophysics. This is the surface geophysics. And over the years, the electrical resistivity method that consists mainly of the constant separation traversing and vertical electrical sounding has proven to be very reliable. You can use to save cost, for example, you don't need to use the electromagnetic. Instead, you can use the horizontal profiling to be able to do the same job. Next. I tried as much as possible just to explain that when you have two core and be driven to the ground, measuring the resistance that is there, the difference in terms of what you have as apparent resistive value is what gives you the value that will help you to kind of identify areas to drill. For example, if you have a topography where one is very high, one is very low, then in between, you can decide to have a 3 vertical electrical sounding at the highest one, the middle, and of course the low. From there, you can now decide to use those values as your constant separation traversing to be able to eliminate areas that are not quite productive. Next. These are just giving you the various, configuration that we're able to. Now, when you have most of the current, for example, the current on C1 and the potential P1 and this P2 are kind of constant, we use that as the Werner array. This is very nice for the constant separation traverse. While the Schlumberger array is very used for vertical electrical sounding. So the more you increase the length of the AB over 2, you are getting more result in terms of what is happening beneath the soil. Next. This gives you a very typical example. Having done your various sounding interpretation, you can come to the office and do the model to be able to put most of what you have from the resistivity values and using the various deck study, because you do not interpret your physical survey results in isolation. You have to use and back it up with the existing data that you have. Next. After the modeling, for example, this is a typical H type of curve where the top of the curve is quite high. What we refer to as the upper resistivity 1 is quite high because of the dry nature of the topsoil. Now, as soon as you keep drilling down, what happens is because a little bit moist and reduces the resistivity because it becomes more conductive until you hit the basement before it starts moving up. Depending on the nature of the fling as you move along, the percentage of inclination, that tells you whether there are presence of fractures or not within the area. Next. Now, this gives you the filter interpretation of what you have the resistivity in relation to the drilling that you are supposed to have. Basically, this is a typical basement complex where the topsoil is quite dry with a lot of laterite. Then it becomes sandy clay until you get to the transition zone that is quite important in terms of aquifer until you meet into the basement. It's only the basement will be useful if it is fractured for water. Next. This gives you a typical example of the most probable resistivity curve you are supposed to have. You have the A type, the Q type, and the H type, and the K type. Most of the time, what it just refers to is that the topsoil here, when it's quite high, as I did mention, the uppermost resistivity when it's heated by the sun, and of course becomes dry, becomes very resistant, the values are likely to be high. And when it comes low, what it means that you have, for example, like clay until you hit the basement before it rises again. So this gives you a typical example of the most likely ones you are supposed to encounter in those areas. And this can be very handy in terms of your interpretation. Next slide. This is also the modeling. You're trying to have example. For example, if you have quite a lot of different scenarios beneath the soil, you can use that interpreting in various, for example, the constant separation traverse in the resistivity Werner array was used, and it can directly identify that in terms of the high value for resistivity, that's where you have the peak. While the other was give you a typical example within the basement of H type of curve, where the topsoil is quite high, and with a little bit of moisture, clay, for example, it lowers the resistivity and before it becomes high. So this gives you a type of modeling that you can use in conjunction with the various logs that you have during your deck studies. Next slide. I've done quite a lot of series of work within it. Within most of the works you have here, we are going to have about 4 more scenarios. The dry basement, for example, which is quite clear at the top, the weather zone and the fresh. Then sometimes the topsoil can also be brecciated or sometimes with a lot of laterite. Then you have the weather zone, then the fresh. Then, or you could have a very clean overburden, sometimes that is mixed up with a lot of boulders, then with weathered basement, for example, and of course, fresh basement with a lot of fractures. The last series is what you have, what I refer to as the force basement. Sometimes you have the top resistance, it becomes a little bit weathered. You think you're already in the basement, the hard rock. And then by the time you case temporary cases and you decide to introduce your hammer, you find that it grinds it down and look as if you are back to the weathered zone of the basement complex. And this is giving you a force, what I call the force basement. So you need to return and remove all those temporary casing and you roll down again before you can now get a hard basement. This is very important. This has resulted into a lot of abandoned wells, abandoned boreholes in most instances. Next slide. Now, this gives you the example of different interpretation of vertical electrical sounding with logs, and of course, give you some model to correlate what you have in the vertical electrical sounding, how they correlate with the drilling that you have. Next slide. This also gives you a typical summary of what you have. So if you have, for example, the depth studies, your recognizant added with the resistivity value, for example, of course, with good drilling, and that gives you the result of good aquifer system and a good borehole. Next slide. Sometimes it's good for you to have an idea of the difficult areas so that anytime you are planning for a very good, where to site bore, it gives you an idea so that almost of your recognizance, for example, and your fieldwork will be based on the areas you are working on. And this gives a kind of advantage over the others, especially if you do not have much data. Next slide. Now, so what are the basic reasons when we are trying to summarize this? Less attention and low investment is normally given to study and investigation stage. This has resulted into very unproductive wells. Geological and hydrogeological difficult area, as I've just mentioned in the last slide. Lack of hydrological maps, satellite images, and software to be able to interpret this. The improper data handling because of the people, you don't have good skills. People experience field people that can help you to interpret data. A lack of regular groundwater monitoring and management system, and generally bad lack of water good quality, and even in terms of the data that you have. This will normally help you if you have good quality data in planning, interpretation, and monitoring. And of course, institutional mechanism is very important for you to be able to do all this. Next slide. Conclusion and recommendations. For you to have an excellent result, there's a need to understand groundwater in terms of the exploration, which is the general ones I've given to you in terms of depth study, recognition, and fieldwork. Then the method of the exploration and the management. Conduct good geological and hydrogeological studies, both within surface investigations and also best site for the survey, drill pilot hole, especially for very good projects that has to do with a lot of boreholes. And of course, you drill and do a lot of geophysical logging to tie most of what you have at the surface with what you're having. And this will give you more confidence in terms of location of groundwater system. Using, for example, the electric, which is the spontaneous potential and the point resistivity, using caliper to be able to notice where you have cracks or loose sand that you have, and of course the gamma that differentiates between clay and sandy formation. Next slide. At the end of the day, it gives you the summary of what you have. You have the geophysical equipment, you have the various surface areas, and of course, coupled with excellent drilling, and you have the result of good aquifer system. Next slide. At the end of the day, sometimes you are sitting or you are standing on a solution, but because you have not taken your time to find out what it is in that place, what are the things that are required, what are the tools for you to be able to do it. And it's normally important for you to find it so that you can use it to be able to achieve your result. Next slide. Thank you very much for listening. And I hope that if you endeavor to adhere strictly to this, you should be able to have a good well at the end of the day. Thank you very much.
Thank you so much, Dr. Oduve. Excellent. Really appreciate just the talk and just allowing us to understand that siting is very complicated. It's not just one point of data and then we move on, but it's really a synthesis of so much work that has to go together. So greatly appreciate that. We have a few minutes for some questions and answer time. And Laura needs to step away, so she won't be able to stay until the final time. And so she's actually going to join Dr. Oduve during this segment while we ask questions. So if you have more questions, go ahead and put them in the chat. And but we're going to start with one from Mohammed Shoaib, and it's actually for Laura. Do we have a checklist to follow while deciding the siting selection? And then a second one, is can we do in locations, excuse me, what can we do in locations where we do not have options for drilling equipment and options for data collection? Laura?
Yeah, they're both really good questions. So
Yeah.
for the first one, I believe Brandon, who's not yet spoken, he works at Hydrologica, and he's shared a couple of documents into that Q&A thread. So that will provide a checklist. But I think in addition to that, I'd just like to say that the key point is that siting is not just following a checklist, and that they're definitely really helpful to make sure that these important steps aren't missed. But I think it's important to keep that message that the quality of the interpretation and the understanding is what really makes the difference here. And then for the second question, again, really important, because in many of the places we work, those constraints are the reality, and I've definitely had those problems myself quite a few times. So in terms of the equipment or rig constraints, I think a key thing to do is really to understand the limitations of the equipment you have. So it just shows how important it is to meet the contractor beforehand and sort of assess their capacity and their equipment, and then factor that into the decisions that you then make throughout the process. So it's about having really good dialogue with the contractor and just figuring out how you can be realistic about, you know, what's achievable in terms of depth or quality of construction. Is there any way that you can slightly design, adjust the borehole design to sort of suit the rig capacity without having really bad long-term negative implications in terms of how the borehole functions? And then I think it's also important to sort of consider if a borehole is the right solution at that location. So you don't, you know, you want to compromise where you can, but I think it's important that you don't want to be throwing lots of money into a situation where you're not going to ultimately have the equipment to do the job at hand. So I think it's just, trying to balance that quite finely. I think that's where this professional judgment becomes very important, and you just really got to work within those constraints and make decisions quite consciously. And then in terms of the second part of that question, where there's a lacking in data, I don't know if it's about pre-drilling data or if it's about the drilling and the data collection during the drilling process. But if it's pre-drilling data, it's just really about making the best out of what's available. I think that kind of shows how important it is to consider these extra field data collection, so hydro surveys, community consultations, that sort of thing. And then if it's about data collection during drilling, I think if you're a bit unsure about the quality of data being collected, it's quite important to try and advocate for a hydrogeologist to be in the ground during the supervision, so that they can sort of help with that data collection process and help with that decision making. Back to Derek.
All right, that's very good. Thank you, Laura. Yeah, I appreciate your answers. We actually have a couple more questions. And the first one, I think, is going to be from Jean-Baptiste. And the question, I think, probably best for Dr. Martin to answer, but you guys can decide. The question is, what is the most effective affecting failure of wells? Is it poor maintenance, poor technology, availability of spares, skilled maintenance staff, governance, or what causes the failures in wells? And then secondly, what can you recommend as well maintenance strategy in areas where well water presents high iron and manganese? So they're a little bit different than what you were speaking about, but I wonder, with your experience, either of you with your experience can answer those questions.
All right. Thank you very much. I think on the issue of failures of well, they're actually a combination of factors, as I did mention. Sometimes you could do everything and there is water in the aquifers. If you do not handle the drilling very well, sometimes it could also be quite abortive. So the design and the final construction matters a lot. Secondly, you could even have aquifers. If you do not locate exactly where you have the aquifers, those could also result into problem. For example, the fact that you have low values in terms of resistivity at the upper part of aquifer does not translate into water directly, because if you have presence of clay, that could also lower the resistivity. So you need to choose what type of resistivity are you working on. And that is why having some good knowledge of the geology and the amount and the resistivity within those areas is quite critical. You also talked about the issue of somebody using geophysics to be able to determine the water quality. Apart from the brackish and, of course, salty nature of the water itself that can lower the resistivity to be very, very low, because remember that resistivity is the inverse of conductivity. To locate whether the values or the areas you are dealing with is actually saline water or brackish. And of course, that has to do with the extremely low value. You need to be able to differentiate how low compared to clay, for example, city clay, for example, and how molten the clay is. These are some of the things you need to look at. He specifically mentioned iron and manganese. And most geophysical methods do not just tell you the presence of this until you do very good quality analysis. You need to have some good experience to be able to do that. Sometimes if you have quite a lot of iron nodules sometimes you will have erratic higher values of resistivity, but this has to do with a very skilled somebody who has worked in those areas, for example. I do know that in some area within the Port Harcourt, the Niger Delta, for example, where you have quite a lot of lateritic values, or in some area where the position of the laterite is quite high, you need a little bit. The value might look very high, but in essence, it is not because of the dryness of the aquifer, but that could be due to the lateritic capping that you have. So these are areas that you need to also look at. I think those are the basic things I can get from what you're saying. Thank you very much.
Yeah, thank you so much. Thank you so much. I did fail to mention that these slides and the recording are going to be available. So if you're concerned that you're not writing down your notes quickly enough, rest assured, the slides will be available. And not only that, but the contact information is also going to be available. So if you have further questions for any of the speakers, you'll be able to have their email and be able to ask questions directly to them and just continue the learning process even after this webinar. So our final speaker is Brandon Stone. He is the CEO and the co-founder of Hydrologica. Brandon's journey into water began way back in 2010 with a Haiti cholera outbreak. And since then, he has built Hydrologica, which is an organization delivering training and consulting across Latin America and Africa, supporting governments, NGOs, and communities in developing water solutions. Brandon?
Hey, good morning, good afternoon, good evening, everybody. Yeah, like Derek said, we provide training and consulting across Latin America and Africa. And then we also have a full drilling operation in Nicaragua. So hopefully we're talking from a position of experience. This is some of the equipment we've got down in Nicaragua. And this morning I'm going to talk to you guys about how to choose the right equipment. Next slide. So matching equipments to the conditions, to the geological conditions is super important. In geology, as I'm sure Dr. Martin can tell you, it gets really complicated. From a drilling perspective, it kind of gets a lot easier. We've got hard rocks and we've got soft rocks. We got swelling clays and stuff too, but ultimately the geology dictates our drilling method. Our borehole diameter is going to play huge into the type of tooling that we have and the size of the equipment that we need, as well as the depth of the borehole. And so we can start to gain a lot of that information from a proper desk study and from a proper hydrogeological assessment. If we just show up to a location with no previous studies or no information or previous drilling experience there, we're not really sure what's down below us, and understanding what drilling methodology we would like to use in that can be nebulous. So this information is important, and when you guys are contracting out drillers, you want to send out all of the studies and all of the information that you have so that those drillers can make an informed decision as to whether or not they're qualified to drill that well. The specifications for the borehole and all of those studies should be made available to the potential contractors. Next slide. So this is our little diagram that we have here at Hydrologica, but the question I think was already raised. How do you drill a good borehole, or rather, why are there so many problems with existing boreholes? And we try to make things as simple as possible. And so we talk about locating the well, drilling the well, and pumping the water. And in each one of those different activities, you need qualified and trained personnel. And they need to have the necessary and correct equipment. And then you need to have a supply chain that supports the spare parts, the materials, and the supplies for that. And so today we're going to talk about, or at least I'm going to talk about the drilling the well part and the necessary equipment that's related to that. It's worth noting that you could have the best equipment in the world, brand new equipment, but if you don't have a competent driller operating that equipment, it's almost completely useless. I'd rather have an older drill rig with a competent driller any day of the week rather than a brand new shiny drill rig. We're actually dealing with that situation right now. Next slide. So there's different equipments, and those equipment, the specific equipment is specific for different drilling contexts. So I'm just going to touch on kind of the most common drilling methodologies. There's mud rotary. There's air rotary, which also includes downhole hammers. It can include foam drilling. And then the oldest drilling method out there are cable tools, which is percussion drilling. And then in some parts of the world, manual drilling is a viable option. Next slide. So one thing we want to do before we contract a driller is we want to assess the driller's ability to drill that borehole. So when we put out a bid for a well and we get bids back from drilling contractors, we want to go and review their equipment. And we want to confirm that the equipment has the capacity to do what we need for that specific borehole. And so we want to consider the capacities not only of the equipment, but of the ancillary equipment, the drill rigs and the compressors and the mud pumps. Next slide. So the drill rig itself, most rigs that are manufactured or that are manufactured by a reputable driller will have published capacities. Most drill rigs, their capacity specifically will include the holdback force, or the capacity to pull things out of the hole. That's directly related to how deep that drill rig can drill. And then they'll talk about the rotary head torque, which is directly related to the drill rig's capacity to drill larger diameter holes. Next slide. So I just mentioned this, but often people ask us, like, how deep can that drill rig drill? And the answer to that is it depends on how much pullback force it has. And that force is related to the hydraulic capacity of the drill rig to move up and down. But more specifically, the capacity to pull weight out of that hole. And what that weight ultimately is the entire drill string, drill collars sometimes, and then the drill bits. And you never want to max out a drill rig's holdback capacity. Usually you want to use about 50% of it at total depth. Next slide. And then the diameter of the well is in part directly related to the drill rig's torque, which is the top head torque, or if you had a table rig. But the drill rig's capacity to turn that drill bit and that entire drill string is related to that top head torque. So the more torque it has, the larger bit that it can turn successfully. And then by extension, a larger diameter well that it can drill. Next slide. And again, all of this can be found either from the drill rig manufacturer, or oftentimes it's printed right on a plate on the drill rig, and we will go out and actually look at that and verify those specifications. Next slide. So the drill rig, there's different rig types, and we talked about those briefly. But if we want to mud drill, we want to make sure we have a drill rig that has a mud pump, or that they bring on an on-site mud pump. And the same is true with an air compressor if we want to drill air. Next slide. And so air compressors are obviously for air drilling. But just like drill rigs, they come in a lot of different sizes. And both air compressors and mud pumps, we want to think about the volume and the pressure. And so can the compressor lift the cuttings out of the annular space all the way to the surface? The larger diameter hole that we drill, the more air volume that we need to push all of those cuttings up. And then the pressure that the compressor exerts is specifically related to hammers. When we're air drilling with hammers, they need a specific amount of pressure to actuate the pistons and function the compressors, the hammers. And then as we drill deeper, we need more pressure to overcome friction losses as we come up the hole. Next slide. And I'll spare you guys the math on that, but you can find it out. We like to recommend an industry best practice is that you have a minimum of 3,000 feet per minute in an annular velocity for dry air drilling. And then so that would convert down to these different CFMs at different hole diameters. So I know a lot of you guys drill 8-inch holes. You're going to need about a 950 CFM compressor to drill that safely. A lot of people drill larger diameter holes with undersized compressors, and you'll get this, hey, the hole's collapsing. No, the hole's not collapsing. There's not sufficient volume to push all of those cuttings out of the hole. So as the holes get bigger, we need a lot more air, or we can turn to foam drilling, which is not something we're going to talk here, but there are methodologies for doing that. The big takeaway here is we want you guys to understand that the larger diameter you have, the bigger the compressor you need. Next slide. And so a similar sizing is true for mud pumps and mud drilling. So then the question is, can the mud pump supply the required volume to get the cuttings out of the hole? And again, this is a matter of volume, and it's a matter of pressure. And all mud pumps should have both a volume and a pressure rating. Next slide. So just like a compressor, the volume is directly related to the diameter of the well. So large diameter wells, certainly 14 inches and up, are typically drilled with mud because it's not economically feasible to put that many compressors in parallel. And typically large diameter holes are drilled with centrifugal mud pumps. And deep wells are drilled with piston mud pumps, and that's because centrifugal mud pumps can generate high volumes, and piston mud pumps can generate high pressures. And so we want, the larger the diameter of the hole is, the larger the mud pump we want, so that we can lift all of those cuttings and that entire column of mud out of the hole. Next slide. And the deeper we go, we're going to need more pressure, and that pressure is directly related to being able to push up all of the cuttings and all of that mud out of the hole. Next slide. And so just wanted to mention, and this is a reality in all the countries we work in, is adapting in constrained environments. So in a perfect world, we would have all of the different equipment options, all of the different drilling methodology options, but that's not always true. So we're always faced by constraints. And as we work, we can be faced with several constraints, and the budget is below the cost of using the ideal equipment. So you need to make sure that your budget is appropriate for the type of well that you're wanting to drill and the geological environment that you're trying to drill in. And then you need to determine whether or not the required equipment is available in your context and in your specific country. And then oftentimes we want to try to validate the experience and the expertise of the drilling company and the drillers with that specific drilling methodology. And unfortunately, oftentimes the ideal equipment is not always available in the countries that we're working with. Next slide. So here's some practical solutions that we often recommend. If you can't find the equipment that you were looking for the borehole that you had spec'd out, oftentimes reducing the diameter of the hole and the casing will get you into the range where the equipment that's available in your context can actually drill that. And then another practical solution is researching successful previous drilling under similar conditions and use that equipment and methodology. So, when we're out drilling, it's not like taking a university exam. We get to cheat and we get to try to copy what other people did. So as a driller, if I'm going in to drill a new area, I oftentimes want to find somebody else that's already drilled there and just simply ask, what did you do? How did it go? And did it work? And then adapt our drilling methodology to what worked for them. Next slide. And so when proper selection is ignored or overlooked, there are risks. And this is what we often find with the consulting work that we do. We get boreholes collapsing, which is sometimes actually a borehole collapsing, and oftentimes is just cuttings falling back into the annular space because the mud pump or the air compressor wasn't sufficiently sized to clear the hole. We could have reduced borehole yields because we weren't able to fully penetrate the aquifer with the existing equipment that we had. We'll have failed drilling attempts because we're not able to drill the geology with the equipment and drilling methods that we have available. And then we can have delayed project completions, oftentimes associated with poor drilling equipment or poorly maintained drilling equipment, and increased project costs because we're continuing to mobilize more and more assets onto a drill site because we didn't fully understand what we were trying to do out there. Next slide. And so these are technical decisions, and this was a extremely oversimplified presentation, as was Dr. Martin's as well. But a successful borehole, we would like to say, always starts before the first turn of the bit. So equipment selection is not just what's available on site, but it's based on calculations and understanding what we're going to drill, depth, diameter, and drilling methodology. It's about understanding the geology that we intend to drill through. And what that means is oftentimes if we're going to drill through a lot of overburden before we hit like a basement rock or a hard rock, we might actually mud drill that top part, case it out, seal it, and then go back in and air drill it because we understand the geology. And ultimately, it's based on the type of borehole we need. Is this a borehole for a hand pump? Or is this a borehole for a municipal water supply? Those will have very different borehole designs and by extension, very different equipment needs. Next slide. That's it. That's what I got for you guys. Thank you for listening to me.
Thank you, Brandon. Love your talk and just very, very practical. And so greatly appreciate it. There's a number of questions that are coming up in the question and answer section. And just a note, if you do have a question, please find the Q&A at the bottom of the Zoom link, not in the chat. Sorry for earlier just confusing that, but want to make sure that all your questions end up there. Whether or not the speakers have time to answer them now, they will be able to respond to them if you put them in the question and answer section. So let's see. We do have a question for Brandon. This actually comes from Brian, and it's an interesting question, and one that I think you'll enjoy. And so don't talk too long about this one, but the question is it ethical for contractors to deny payment to a drilling contractor solely because the drilling well produces less than a specified amount of water?
Yeah, man, we get this question a lot. And I'll tell you what, as a drilling contractor, we specifically put in our contract that we are not responsible for water, the yield of the well, neither the water quality. I think the drilling contractor should be paid for works completed. So what this requires is it requires a competent client, and then it requires competent supervision and a competent driller. You can have the best study in the world, but geophysics is still an applied science. It's still an estimate. And as we go in there and drill, we would typically drill a borehole and then have a crude estimate of what that's producing, especially for air drilling. And then we wouldn't necessarily case out that well unless we thought it was likely to have a sufficient water supply. If that's the case, then we only charge our clients for the mobilization and the drilling of that. But drillers should be paid for the work that they completed. When you don't do that, what happens is drillers are incentivized to quit drilling early because their risk for drilling deeper means that they're assuming more and more costs without getting paid. And a lot of boreholes, and I've seen this across Africa, there was an aquifer down there, but you guys never got to it because that driller is afraid he's not going to get paid. And so they ended up being failed boreholes simply because they were too shallow, not because there wasn't groundwater there in that specific location.
Thank you. Thank you. Let's see. This could be answered, Brandon, by you or by Dr. Martin, but can you share how satellite and GIS data can be used within the siting process?
Yeah, I can answer that real quick from our end. We use that for fracture tracing. So before we ever go out to site, we'll just take a look at a site topographically, and we'll use GIS for that to better understand what's going on there. But that's my drilling perspective. Dr. Martin can say something much more eloquent, I'm sure.
Yeah, let him jump in here.
Yeah,
came on.
You're very right. We can definitely use that, but sometimes it's subject to what you have. You do not do it in isolation. That is the point there. You don't do it in isolation. You have to actually use other data to be able to complement that.
Okay, thank you. Sorry. Brandon, back to you. Here's another question from Hastings. Will reducing the diameter of the hole not affect the amount of water you desire to have from the well?
That's a great question that we get a lot. And I would say it's not much. My understanding is a 6-inch diameter borehole compared to a 4-inch diameter borehole actually only produces about 10% less water. What it affects is your ability, what size pump you want to put in there. So people often misunderstand this. They think a larger diameter borehole means more water. It doesn't mean more water. It means a larger motor, which is typically related to total dynamic head. that we're trying to pump out of there. So we usually work backwards from what size pump are we going to put in there to determine borehole diameter.
Great. Yep. Thank you so much.
Sorry. In addition, sometimes you have to also look at the cost. You have to also look at the cost. Yeah, I'm only saying that in addition, because if you decide to use a 12-inch hole, for example, that borehole will be much, much higher for the 12-inch because of the materials you are using to produce that. But if you have 6 inches hole, as Riley pointed out, my colleague, the cost, the increase in terms of the yield is not more than 10%. So is it worth it for you to pay $1 million for a 12-inch borehole and pay $500 for a borehole that you're going to get plus minus for 10% in terms of yield? So it's very important that we get it very clear. The size of the borehole does not significantly increase in terms of the yield. It's not less more than 10%.
Thank you, Dr. Mo.
Yeah.
We have another question that came up for Brandon, and it's a very basic question, but important, is who's at fault when the borehole fails?
Sorry?
It depends.
The question is, sorry, I said it maybe too quickly. The question is, who is at fault when the borehole fails?
It depends on why it failed. I could tell you the driller always says it's the hydrogeologist, and the hydrogeologist always says it's the driller.
So Dr. Martin is blaming you, and you are blaming Dr. Martin.
Yes, it's Dr. Martin's fault typically. Yeah.
All right.
He could, you know,
at the same time,
there's no easy way to answer that.
Sometimes we have what we call not.
I've seen boreholes that have failed because of it's a siting issue. Siting is often a common issue, or like hydrogeological studies, or people love to just hire a geophysics company to go out and do geophysics without any thought involved in it whatsoever, and then the geophysics aren't even complete. I've also seen people hire air drillers to go out and drill alluvial basins that needed mud drilling. And so it's really situationally it's situationally dependent. What you need, back to that original slide, is you need a competent, trained hydrogeologist to do your site selection, and then you need a competent and trained driller to appropriately drill it. When you do that, just for the record, when you do that, you should have over an 80% success rate. Our success rate drilling in Nicaragua is between 80 and 87%. We've replicated that in Africa, and that requires proper siting, and it requires proper drilling, and all of that costs money. So if you start with your budget, you will fail. If you start with, hey, we want to get water to this area or this section of a country, and then you say, here's the studies that we need to do, and then you say, here's the drilling equipment and methodologies that we need to drill that, you will have a much higher success rate.
Yeah. Just one more issue there. Sometimes you will have a geophysicist who have identified the fractures. What I mean by that, you could have a fracture and a fracture might not be productive, but the geophysicist or the hydrogeologist is looking for fracture. Technically, he has identified the fracture, but how much water do you have within the fracture? Nobody can do that until you do the pumping test. It's the same thing that is applicable to the driller. If you put all the conditions and all the conditions are well to do and everything is in perfect condition, and sometimes You could have everything. If you do not maintain some of these things, like the materials you are putting in, take the issue of gravel, for example. If they are not well sorted, or you have gravels that are derived from crushed rocks, you do not expect the yield to be the same. So there are a lot of possible. It's a very big, difficult task to actually pinpoint, but we should do the right thing.
All right, thank you. Let's go on to another question. This question, I think, also could be answered by either of you. So thank you for both being here and answering these questions. The question is, what could cause a borehole to cave? Recently, I surveyed a site where they encountered open space between, I think it means a depth of 33 to 40 meters, and then at 45 to 49, they struck water, but then the following day it was dry. What could be the reason for that? Let's let Dr. Martin start.
Yeah, there are quite a lot of reasons. It's possible that what he was thinking that is actually an aquifer is not even a good aquifer. Sometimes you could have clays, and when you have the clays that are not properly sanding in terms of good aquifers, you do not, the water, it will contain water, but you cannot extract it. And that's why we are saying that an aquifer is a geological formation that can store and be able to transmit. Secondly, it's also possible that at the peak where you have the aquifer, you did not design the boreholes very well. So instead of putting screens directly opposite the aquifer, you went and blocked it with casings. And what it means that you might not be able to have easy movement of water directly, especially if you do not have any screen at the bottom where the water can go within the annular space and enter through the last screen before you did the casing. So there are quite a lot of factors that could also happen. Secondly, or thirdly, you could also have some what we call aquifers where the fractures are limited. And at the time you drilled, some fracture might be passing with some good water, but they are not extensive. So as soon as that water leaves, the whole thing gets blocked and there's no more water. So there are quite a lot of issues that can be responsible for that.
Brandon, do you want to comment also or add on to that?
Yeah, and again, it's really specific to the actual geology. So like I mentioned previously, if you're trying to air drill in alluvium, in sands and gravels, it's going to cave in. The only way to properly drill alluvium is with mud. And then the same is true. I mean, you can have really stubborn formations while you're air drilling as well, in hard rock with fractures, especially larger fractures. But it's pretty specific. I think most of those problems are solved by starting off with the properly sized equipment. We see a lot of times people trying to drill large diameter holes with undersized compressors. And we see people trying to drill deeper holes with undersized mud pumps. And both of those don't cause borehole collapsing, but that equipment isn't designed to, or doesn't have the capacity to lift the cuttings out of the hole, and it ultimately falls back on the drill bit and causes what people think is a borehole collapse, and it's not. It's just a failure to get the cuttings out of the annular space.
Great. So important just to have the right equipment. All right, we have many questions coming in, and fortunately, we still have some time. So I'm just going to keep on putting you two gentlemen in the hot seat. The next question is specifically for Brandon. And I'm looking here, and oh, here it is. Is there any matrix that could help us to choose the best drilling option based on site conditions, soft rock, hard rock, etc.?
Yeah, I have a drilling matrix that we can share with you guys. And it shows different drilling methodologies and the appropriateness for different geology. happy to share that.
Thank you. Yeah, that'd be great. And this question is for Dr. Martin. Geophysics data is really an indicator for groundwater investigation. So maybe I need to rephrase that question. Is geophysics data really an indicator of groundwater investigation? In Ethiopia, some bore well investigation was done by a geophysicist, and the result of the data of the study was that water will be available on the site. However, during the drilling, there was no water. What could be the possible error that caused this?
Yeah, thank you very much. I think I've mentioned it before, depending on the geology. If, for example, you are drilling in a fractured rock basement complex, and you have the fracture, because that is what the geophysicist, the hydrogeologist is looking for. You have the fracture, and that will decrease the resistivity that you have within the area. You could have fractures, but the fracture might not contain water. And of course, you go and drill, the fracture is there, but it's kind of, there's no water within the fracture. So that can also be responsible. Secondly, it's also possible that they've done the geophysics and they've asked you that for you to get to the aquifer, you must drill to, for example, 350 meters. And the equipment you carry to that place, the drilling rig, has the capacity to drill just only 200 meters. So after drilling, you do not expect to have good water within the area because you've not achieved that drilling depth with the bad selection of equipment. So that could also be responsible for it. Then also the designing within the borehole itself. If everything in terms of geophysics is correct, the drilling is correct, and you decide to shift the aquifer positions, you do not expect to have good water. So there are quite a lot of factors that could be responsible. But the good thing is that when you are doing any geophysical, any borehole siting for borehole drilling, you must be able to do a combination of all the factors: surface geophysics, previous data, well logging, for example, to be able to identify exactly after the drilling, so that it will help you to have actual design of the borehole that will give you a productive borehole.
Thank you very much, sir. We have a couple of questions about GIS and using things like Google Earth and things like this. So let me see if I can find that question again. So the question is, how do we access satellite data for groundwater investigation? And then how does the GIS data actually help in finding the water source?
Thank you very much. I think this has to do with looking for the specialists that can interpret those satellite data. For example, aerial photograph or satellite. When you see fractures within that, it's only the people who have been trained to be able to do that, we're able to identify where there are fractures. Now, if you do not take into cognizance, because you have aerial photograph and you feel that you know everything, then you are wrong completely. So they have to be the special that we are able to identify and interpret most of those data, either it is from satellite, aerial photograph, and all existing borehole data, including reports that we translate into a productive siting techniques that we have.
And then Brandon, I have a question for you. And it is, can you just explain what cases where mud drilling is better than air drilling or vice versa?
Yeah, and I just dropped that matrix into answering that question. But anytime you have an unconsolidated formation, mud drilling is the appropriate methodology. And in fact, you can actually drill anything with mud. It just gets really slow. And that's not the case for air. So it's better to say air drilling is only recommended when you have a consolidated or a hard formation that's not going to collapse on itself. And I realize, and we do this too as a drilling company, we cheat on that all the time. And we'll air drill stuff that is kind of going to collapse, but we don't really want to mix up a bunch of mud. And so we'll air drill that out real quick and maybe drop some casing down there. But anytime you have alluvium, if you're planning on drilling sands, if you're planning on drilling gravels and some sorts of clays, you're gonna need to mud drill that. And then any of your harder rocks, typically from sandstones up, you can successfully air drill those. But we will, and what I advocate for is we will oftentimes drill both methods on a borehole. Oftentimes we will drill out the overburden with mud, and then set a permanent first string of casing, grout that out, and then we'll go back in and air drill to total depth after that.
Great. Yeah, thank you. And then maybe a question for both of you. Is it possible to check iron levels? So we're kind of moving it. This question is a little bit in the water quality field before the borehole is completed.
The answer is no from the result. But if you have previous data of the area, it will give you an idea of where this area you have quite a lot of iron or you have a lot of manganese. That will help you. But identify directly from the either geophysics or that is practically impossible to do that. But by experience, when you see, for example, a laterite, you'll be able to see from the iron that is directly affected when it's so brownish and all that. And of course, when you fetch the water, you put it in this, it turns, because of the oxidation that is taking place. As soon as the 02 is react with oxygen, of course, most of those ferric this thing comes in and you can see them directly. Apart from that signal, it's very difficult for you to identify until you carry out water quality analysis.
Yeah, thank you. Until you actually can get to the water, you really don't know unless you have another well nearby where you can do a comparison.
Yeah.
Another question for Brandon. It's an interesting one. Can you use if your single mud pump doesn't have enough power, can you use mud pumps in series to boost it?
You can if there's centrifugal mud pumps. So centrifugal pumps can be put in series and or run in parallel. Piston mud pumps, however, can only be run in parallel.
All right. Thank you. All right, we keep having questions coming, so thank you very much, gentlemen, for staying on, and I'll keep fielding some questions. This question is somewhat similar from Ronaldo, similar to another question, excuse me. Whose responsibility for contracting the siting consultant, the client or the contractor? In my country of Mozambique, contractors do. And they don't pay enough for the consultant to follow the complete procedure because they are not paid when drilling is unsuccessful. Who would like to answer that first? Dr. Martin?
Okay, I think it depends on the nature of the contract. For a very small project, for example, you do not need that elaborate consultant and of course the contractors. But for very big projects, you're going to have the consultant who normally does the formulation and the rest of them. And of course, he also does the supervision. So of course, before the contractor can collect any money based on what is done, you need to certify. So it depends on the nature of the project and how huge, or for very small projects, consultants don't even have very good place in it.
Brandon, do you want to comment on that, or?
I think he covered it.
Okay, I saw your movement and I just wanted to make sure I didn't cut you off. Thank you very much, Dr. Martin. Another question about collapsing wells has come in from Susan, and it is collapsing of a drilling borehole only associated with a soil type, And then another kind of associated question with that is what kind of casing is best recommended for areas where the soil is more sandy?
Yeah, so I know we've touched on this already, but most of the collapsing I've seen that I think most of you are referring to is where organizations or companies are trying to air drill in alluvium, and the sands and gravels are just falling in, and it's a matter of having the appropriate drilling method for the geology, and mud drilling. It would be the appropriate methodology for stabilizing and drilling that borehole. In terms of casing type, that is typically more related to depth, and there are casing collapse pressure calculations that you can make to determine the schedule or the wall thickness of your casing, as well as the material type for a certain borehole. I'm happy to share those. We've got a technical data sheet on that we could share. But in so much as possible, we prefer to use PVC casing as long as it's within the appropriate standards for the casing collapse on that, because it doesn't corrode when we have corrosive water. The screen doesn't foul up as much, and then it makes for a more economic well. So, yep, that's my comment on that.
Thank you. And I have a question.
Sorry,
I saw this one previously. Yeah. Oh, excuse me, Dr. Martin.
Yeah, just one more point. Sometimes the nature of the chemicals for the drilling also matters. If you have, for example, custom mud that is not very, very, very good, the tendency is that the viscosity tends to kind of decrease faster. Secondly, when you also have aquifers that is so prolific, very productive, so that means that you have quite a lot of water trying to mix up and dilute the density of that mud. And when you have a situation like that, the rate of collapsing is much, much higher. So sometimes we have to provide additional custom mud and also add viscosity, what we call improver. You could decide to use, for example, the husks of rice. We've used that before. You try to mix it up to increase the density and the viscosity of that particular mud. And that will help to kind of reduce the collapsing of the hole. So these are some of the little things that you can do to improve and reduce to the barest minimum the issue of collapse, especially when the aquifers is so prolific.
And maybe associated with this, are there any special, if you're drilling near the ocean, is there any special considerations, one for siting because of the salts and maybe also a high saltwater level, and then for drilling?
Yeah, when we drill anywhere these days, we always monitor the electrical conductivity. Either if we're air drilling, we'll monitor that after our first water strike. And that's not necessarily representative of the final borehole quality, but we use that as a baseline, and we can watch conductivity and see if it's going up or down. And so if we're drilling, and we've drilled wells, within 30 meters of the coastline and gotten fresh water at 200 meters. And we've also drilled extremely saline wells, 10, 15 kilometers in. So I know that depends on the hydrogeological condition, but we constantly measure the electrical conductivity. We'll actually do that on our mud drilling as well. And again, that's not representative of the final water quality, but we can use that just to see if there's a change over time. And then ultimately make an inference from that.
Thank you.
Sorry, one more point there. We also utilize well logging using the electric. If you use the resistivity as you look along, you can identify directly the issue of saline water within what depth does it occur and so on. So if you have that, you can decide to identify straight away. Then the hole must be big. And what we normally do is to backfill everything with cement and bentonite and allow it to settle. Then you re-drill within that. That will eliminate most of the saline water that is coming to the borehole. We've done that in riverine areas in Port Harcourt and the rest of them before in the Niger Delta area. So those are also some areas you can also prevent a lot of those brackish and saline water intrusions.
All right, thank you, gentlemen. We have a list of about 500 more questions to ask you, but unfortunately, we're coming to the end of our time. So first, I want to just thank you, gentlemen, for preparing and taking the time also to present and answer so thoroughly these questions. And Laura's not here, but we should also thank her for the investment of time also. And then for all of you who've been asking questions online, greatly appreciate it. You can continue to ask these questions, and I encourage you to, if you have more just directed questions, that you can grab the contact information from the speakers and directly email them. I'm sure that they will be very happy to assist you where they can. Brandon, one question that came up was on formal qualifications for drillers. I think that you have that written out. So you probably, we don't have time, but it might be also another thing that you put in the chat box, or if Dr. Martin has the same. It would be very helpful to have such documentation just to help people as they are presenting, or as they are trying to find competent drillers. But as you have stated, you know, the importance of finding just really good quality equipment and making sure, verifying on the ground that that equipment is high quality is very, very important. But even before that, we just want to again emphasize just the importance, as Dr. Martin shared, about the importance of proper siting. You really, it's not just a go and guess, and this looks like a nice place to drill a well, but it's very technical and it's a critical role that needs to be played. And then we need to make sure that we have just a matching equipment to the conditions, whether it's mud drilling or air drilling, or as Brandon mentioned, oftentimes both. And then we also just need to make sure that we're sharing, you know, all this data together, and so that the person who's doing the desk study shares that well with the person who's doing the siting study, and then the geophysicist working together with the driller closely, and takes an awful lot of collaboration across all of these different channels. And so thank you very much for participating in this webinar. Finally, I did want to mention that this webinar is going to be available. You can just download it from the website. The documents that both Dr. Martin and Brandon have prepared, the slides will be available, as well as some other documents that have been requested. The speakers will put there. And then at the very last, I want to make sure that you take some time and fill out the webinar survey, just to help us as we're trying to continue to improve these. And then finally, I just want you to know that this is actually the first of 6 excellent webinars that are being hosted by the Rural Water Supply Network. And so I encourage you to join in. Next week, we have 2, and then we have 3 more in June. So thank you very much for your participation, gentlemen and Laura. And thank you very much for participating, all that joined this time. Thank you very much for being here.